Continuing in 6.2, let's look at some examples. So let's write this down. The region bounded by y equals x squared and y equals x plus 2 is revolved about the line x equals 3. Find the volume using the shell method. So in this case, we want to revolve this. So I went ahead and graphed it, right? So here's x squared. So this is a little different setup because it's a different revolution. But the concepts are still there, it's still the same. And then the line y equals x plus 2 is this. So I took the liberty of graphing those earlier. Do those on your own and make sure it makes sense to you. So then to find that area, you would do the little rectangle, right? Representative rectangle is what we call it. And your thickness would be the delta x. And the height would be the difference of the function values. So that's like your altitude. So let's fill in the blank here what these are. So the thickness is your delta x. Okay. The average radius will be basically this piece here. So it's from the center of the revolution to wherever the middle of that representative rectangle is. So if you call this x, that goes from the vertical axis, the y-axis, to x. But that's not what we're looking for. We're looking for this distance. So this distance here, and if we start at 3, is 3 minus whatever this x is. So 3 minus x is the average radius. Okay, then the altitude is like before. That's going to be the height of the whole thing. That's your h. So that is the difference of the function values. The top one is x plus 2 minus the bottom one, which is x squared. Okay, then let's set up, I'm going to take this in a little bit here. Let's set up our function. So our volume then is what? So volume equals, and now we're going to integrate from where to where. So we would need to know what this is, that intersection. And you can see that that's just 1, right? So if you get, if x is 1, y is 1, and so I'm looking over here. If x is 1, y is 1. If x is 1, oh, I'm sorry, -1. If x is -1, y is 1. If it's -1, y is 1. Okay, so you can just test it real quick. So -1 does work algebraically, not just graphically. All right. Okay, so then we can see we're going to integrate from -1 to 2 all the way across. And then we're going to be revolving that around the axis like that. So on your integration, you're going to integrate from -1 to 2. Then it's 2 pi. That's basically going all the way around. And then it's the average radius, which is 3 minus x. And then times the altitude, or the height, which is x plus 2 minus x squared dx. Okay, so work that out and simplify it and see what you get. And hopefully you got something like this. Okay, I did it earlier. Okay, so I duplicated this, but this and this. So we worked it out, just multiplied it out, simplified, substitute, and then I verified it on Wolfram Alpha, just because I didn't want to have to do all this arithmetic. But so I went ahead and used some computer algebra systems to simplify it and take a look myself. Okay, next question. You take a look at that. positive. So you can pause it, and now let's move on. All right, so next one. Let's see, I'll go ahead and write this one up from scratch here. So the region bounded by y equal to 2x minus x squared and y equals 0, that's the x-axis, right? Is revolved around the y-axis. Find the volume, or find the resulting volume, or find the volume of the solid. Sometimes how they say that. So let's take a look at first the y equal to 2x minus x squared. So what we really want to do is graph this and see what it looks like. And to do that, we want to complete the square and put it in the form x minus h squared plus k, because it's a quadratic. So let's rearrange it to negative x squared plus 2x. And then factor out the negative x. We get x squared minus 2x. Then we're going to take half of that and square it, add it there, and then it's going to be plus 1. So this is negative 1, so you got to add the opposite. Okay, so that factors to negative x minus 1 quantity squared plus 1. So that's the form a times x minus h quantity squared plus k. So we know the vertex then is hk. So the vertex is 1, 1. Okay, and it opens down, right? It opens down like that. So because a is negative 1. Then we can factor. Let's see, going back to the original one. So we can factor, so 2x minus x squared, we can find the roots. Factor out an x and you get 2 minus x. So the roots are 0 and 2. Okay, so we're doing good here. Let's go ahead and graph that. Let's do it right about here. We'll make this, so it's shifted. Oh, I should just move that. It's shifted over. So I'll do it like this. So the vertex was 1, 1. So and then it's over at 2. So we'll just make this 1. This 2, and then 1, 2. So here, so do it like this. So this is our graph. Like that. Not real parabolic looking, but it's okay. And we're only interested in between the x-axis and that value. So put in my little x, y's. Can't really graph without those. That's 0. That's 2. This is a 1. This is a 1. Okay, just verifying how we had it. So that region is revolved about actually I forgot. Hold on a second. What is that revolved about? the y-axis. So we're going, we're taking that thing and you're coming out at you and revolving it, or back and revolving it. So it's creating a shell or a volume that looks like this way. Okay, so let's then go to this. So the volume is going to be the integral 0 to 2. Oh, and do you see how using the shell method is really the preferable way to do it? Otherwise, we'd have to use washers like this, and those well, no, not like that. Those washers would be this way. And then you have an outsider. So you'd have to change it to delta delta y's. Well, this one you can keep it in terms of delta x. So if we put in a representative rectangle here, like this, that becomes a shell. And you still have dx, or delta x. Otherwise, you're going to have to go across like this and change it to a delta y. I don't really want to do that. Not with, because you have a square root. Yeah, it wouldn't be very fun. So our form is 2 pi. I picture the 2 pi as like the circle part, right? And then average radius. And then altitude. This is kind of what you would write down on a note card if you had a class like that. You'd write that part down because that's what you need to remember. Not like the f of x's and all that. You got to think in terms of more general concepts when you're doing these. And so the average radius, this one, what would that be? Take a guess on that one and your altitude. Okay, this one's pretty straight up, right? This one's pretty straightforward. This one is just your x because this is your distance here. So you're going like that. Let's do it like this. So that's your radius, or your average radius to that value x as you're revolving about that line. Okay, so there's your x. And then your altitude is just that height. So your h is just going to be the function value. So the function value, or the function itself, because it changes as you move across. Okay, so write that down. What's that going to be? That's going to be equal to the integral 0 to 2 pi, and then x, and then times the altitude, 2x minus x squared dx. Okay, so let's go ahead and work this out. What was I going to show? Oh, I was going to tell you something. I almost forgot. I worked out that one. I also worked out this one above, I think. Was that it? No, I did that one. This one. So this one, I don't know if I worked it out originally, but this I did it later. I got that. Okay, and then so let's go through this one. I wanted to show you a couple things here. So we get this is equal to, and then factor out the 2 pi, and let's go and evaluate it. No. Yeah, I'm gonna go and do a couple steps. So 0 to 2, 2x squared minus x cubed dx. And now I can evaluate it. So 2 pi, and then it'll be 2/3 x cubed minus 1/4 x to the 4th, evaluated from 0 to 2. And since it's a polynomial, 0 will zero everything out. So we're just substituting in 2. So this is equal to 2 pi times 2/3, and then that's 2 cubed. I know that's 8, but whatever. Minus 1/4, and then 2 to the 4th, and then I'll just say minus 0. So it's 2 pi times, that'll be 8 times 2, so 16/3, minus, and then 2 to the 4th is 16, right? Because it's 4 times 4, so 16. Or one way to do this is 2 to the 4th, 2 squared, but that's over 4. So it's 4. So minus 4. So 2 pi 16/3 minus 12/3. Don't use decimals. Do not get to decimals, please. There. Work it out by fractions and leave your pi in there too. So that'll be 2 pi 16/3. Oops, I gotta actually evaluate that, huh? Let's go ahead and do that. So 16 minus 12 is 4. Right, so 2, 3, 4, 5, so 4/3. So that's 8 pi thirds, or 8/3 pi. Does it make sense? It isn't negative. That's something. Yeah, that seems right. Okay, I wanted to show you this. You can evaluate this using Wolfram Alpha. Let me show you that. Go to math. There's other ones. There's all kinds of ones on there. There's different stuff. So I'm going to see if I can get this to work. Okay, so let's see. What do I want to do? Integrate. And then write in the function. I'm gonna keep off the 2 pi. We're just gonna do the x part. So we'll do x parentheses 2x minus x squared, close parentheses, oops, close parentheses, verify, so integrate x times 2x minus x squared, and then all you gotta do is say this from 0 to 2. Let's see what it gives us. Gives us 4/3. So it shows you the integration. So you can double check that if you want. So let's do this. I'm going to take a screenshot of that. Let's see. We can verify that with 4/3. Just write down 4/3, and you can verify the integration itself, and then double check. And so what do we get? 8 pi thirds. So yeah, that looks right. So one way to do this. Let's see. Oh, that's okay. Let's just go back. So there's your 4/3. Right, that's what you got. So then you just simplify it. On something like this, though, you would need to show your integration, and at least like up to here. Once you do that, the rest is really arithmetic, which, ideally I want to see everything I'm writing, but I'm not real picky on okay, you just evaluated that somehow. But I do not want decimals. Okay, so no decimals. So we want exact form. Okay. All right, moving on next to 6.3 is arc length. I will go through the derivation of the formula. It's a good one to go through. There's a lot of good stuff in there, using the mean value theorem and some derivations, mostly for the class focus on evaluating the the arc length of something. But we'll go through the details. Until next time.